Welcome. Today we're diving into the SOLID principles, 5 essential guidelines for writing clean, maintainable, and scalable object-oriented code. SOLID stands for single responsibility, open-closed, list of substitution, interface segregation, and dependency inversion. Each principle helps you design better software by reducing coupling and increasing flexibility. We'll walk through each principle with clear Java examples, showing both what to avoid and how to do it right. Whether you're a beginner or brushing up your skills, understanding SOLID will transform the way you approach coding. Let's start by exploring the single responsibility principle and see how it sets the foundation for robust software design. Let's begin with the single responsibility principle, or SRP. This principle states that a class should have only one reason to change, meaning it should handle just one responsibility. For example, imagine a bank account class that manages deposits and withdrawals but also generates account statements. This mixes two responsibilities, account management and reporting, making the code harder to maintain. A better approach is to separate these concerns, keep bank account focused on account operations, and create a statement service class for generating statements. This way, changes in reporting don't affect account logic and vice versa. SRP leads to cleaner, more modular code, making your projects easier to test and extend. Next, let's talk about the open-close principle. This principle says that software entities should be open for extension but closed for modification. In practice, this means you can add new features without changing existing code. For instance, if you have an interest calculator class that uses if-else statements for different account types, adding a new type means editing the class, a violation of OCP. Instead, use interfaces and inheritance, define an interest policy interface, then create separate classes for each account type. Now, adding a new type is as simple as creating a new class. This approach keeps your code stable and flexible, making future changes less risky. Moving on, the list of substitution principle ensures that subclasses can stand in for their parent classes without causing errors. For example, if your account class allows withdrawals, but a fixed deposit account subclass throws an error when withdrawing, you're violating LSB. The solution is to design your base class with only the methods that all subclasses can support. In this case, make account an abstract class with a getBalance method, and let only the appropriate subclasses implement withdraw. This way, you can use any subclass wherever an account is expected and your code will behave consistently. LSB helps maintain reliability and predictability in your software. Interface segregation principle advises us to design small, specific interfaces rather than large, general ones. This way, classes only implement methods they actually use. For example, if you have a banking operations interface with deposit, withdraw, and apply for loan methods, a loan account class might be forced to implement deposit and withdraw even though they don't make sense for loans. The better approach is to split the interface into deposit operation, withdraw operation, and loan operation. Now, each class only implements what's relevant, leading to cleaner and more maintainable code. ISB keeps your codebase focused and avoids unnecessary dependencies. Finally, the dependency inversion principle tells us to depend on abstractions, not concrete implementations. High-level modules shouldn't be tightly coupled to low-level modules. For example, if your account controller directly creates a regular account service, you'll have to change the controller if you switch to a premium account service. Instead, define an account service interface and let both regular and premium services implement it. The controller then depends only on the interface, and Spring injects the right implementation. This makes your code flexible and easy to test, as you can swap implementations without touching the controller. DIP is key for scalable, maintainable systems. Wrap up: mastering the SOLID principles will help you write code that's easier to maintain, extend, and test. By following single responsibility, open-closed, list of substitution, interface segregation, and dependency inversion, you'll avoid common pitfalls and build software that stands the test of time. Remember, these principles aren't just theory, they're practical tools you can apply to real-world projects, especially in Java. Keep practicing and you'll see your code quality improve dramatically. Thanks for joining this journey through SOLID principles. Happy coding!